All right, here we are with day 19 from Advent of Code 2022. Once again, I thought this was one of the harder problems in the whole set. It's very similar to day 16 in that it's also a graph problem. We also have to take some steps to avoid the search space becoming too big. We'll see how all that develops. Let's go through this problem description. Basically, we need to collect a series of resources using robots, and we eventually want to mine geodes. But the trick is that in order to mine geodes, we need special geode robots. In order to build geode robots, we need to collect obsidian and ore. To build obsidian collecting robots, we need clay and ore. And to construct clay robots, we just need ore. So we have this hierarchy of resources, and we need to allocate our resources so that we can build more robots and so that we can collect more resources. It kind of reminded me a little bit of the game of StarCraft, where you have all of these different worker units, and you have to collect minerals, you have to collect Vespene gas, and you need to make sure you build supply depots, or of course pylons, in order to make sure you have enough what's called supply to build more units. So kind of like that, we have a lot of different resources and constraints that we're trying to balance. But ultimately, we want to search for the construction that gives us the most geodes at the end of 24 time steps. At least it is 24 in the first part of the problem. It becomes 32 in the second part. We'll get there when we get there. Let's jump into the code. So this is what our input looks like. Each line of our input is a blueprint. So a blueprint tells us how expensive it is to construct each type of robot. And so we can use the blueprint to configure our factory once, and then we have to stick with this blueprint for the rest of the run. So we're just trying to find the optimal blueprint. Or it's actually, it's going to end up being a little different than that. But the point is we want to find out how many geodes we can mine with each of these different blueprints. So parsing these blueprints isn't that difficult. It's a lot of strings. So we say blueprint, and then we parse a number, and another string, parse a number, etc., etc. Ultimately, what we gather for each blueprint, we have an ID number, because we'll need that to get our final answer. But we need the cost of the ore robots, so it requires ore to build ore robots, and we start with just one single ore robot. And then we have clay robots, or we need the cost of the clay robot that is parsed from the blueprint. Clay robots require ore to construct. Obsidian robots require both ore and clay, so they have a tuple of integers here. And then geode mining robots require obsidian, and they require ore. Actually, I think I put the ore cost first for both of these. So this is an ore value, this is a clay value, this is an ore value, this is an obsidian value. So that's how we describe our blueprints, that's how we parse our input. Now, let's move on to the solution. As I said, we're going to map this as a graph problem. So we're going to perform a search, and we're going to try and find the search state that results in the optimal number of geodes that we can mine. So every graph problem, we have some sort of search state that we are keeping track of. So the relevant items in our state, we need to know how many of each type of robot we have. And then we also need to know how many of each resource we have. So this is the number of robots that are mining those resources. These are the resources that we have on hand, because we might not be able to spend all of our resources. We also need to know the time step so that we know when we're sort of done. Now, the root, or I guess the most important piece of any graph problem, the root of the graph problem is our search state. The most important piece is how we calculate the neighbors. How do we take one of our search states and determine what other search states we can go to from there? And what we'll need to do in order to get a solution relatively quickly is we'll need to be very smart with how we calculate neighbors, because we need to do some degree of pruning. Because if we explore every state, it's going to take too long. So there are going to be a couple different pruning tricks that we will apply here. So the first pruning trick is that we're going to calculate the largest number of geodes that we could possibly mine from this particular search state, and we're going to compare that with a previous maximum value. So we'll see how this works in in our depth first search that we're going to apply later, but we will have some previous max number of geodes that we've calculated, and then we will calculate the most that we could possibly get. So there's a very optimistic value in the sense of, okay, we'll take the current number of geodes, we'll assume that we can construct a geode robot for every time step from now until the end of time, and we will assume basically that each of those robots will progressively collect more geodes. And so what this ends up being, so we have the current number of geodes, we have the number of robots times the remaining time, and we add the sum. I think this is actually sort of, there's like a triangle number going on here, but that's what this calculation is. It's saying what is the most geodes we could possibly mine from this position. If that is smaller than the previous max we've achieved, then we're just going to return no moves. We're going to say this search state, we don't care about it because it's not going to get us our best answer. So this is very important because we need to prune our search. So the next thing we're going to do is we're going to look into some of the possibilities of, so I guess there are two ways we can actually move. One of the ways is simply to step time. So we can either build a robot or we can not build a robot. We can't build more than one robot on any given turn because we only have one robot factory, but we can choose to not build a robot. And so that is what step time means. That just means we say t equals t plus 1, and then we just mine our resources. So the amount of ore increases by the number of ore robots we have, the number of clay items we have increases by the number of clay robots, etc., etc. So that's what stepping time looks like. That's basically always an option as long as we aren't doing this premature pruning. We will always have step time as an option. And then we'll also consider the options of constructing the different robots. So we can try to make an ore robot on every turn. And there are a couple things that come into play here. We'll have an extra level of pruning with each of these options. So first of all, we need the amount of ore that we're holding in our search state. So that's up here. We need that to be greater than O. What's O? That comes from the blueprint value. So O is the amount of ore needed to construct an ore robot. So in order to do this construction, we need to have enough ore. That's what the first part of the condition is. Now the second part of this condition is actually stating this idea. We don't want to build too many ore robots. We can only spend a certain amount of ore every turn. So we can take the maximum of however many resources it takes, however many ore it might take to construct any one robot. We take the maximum of that. If we already have that many ore robots, there is no point in building any more ore robots. And so we'll actually do a level of pruning here. So if this is greater than or equal to, we will never build another ore robot. So we need this condition to be satisfied. If that condition is satisfied, then we will do the same thing as our step time search state. However, we will increment the number of ore robots by 1. We will subtract the amount of ore that it took to construct that robot. Those are the changes that we'll make. So this is really sort of one of the key pruning steps we take, and we do this for all of the other different robots as well. So we can try making a clay robot, so we need obviously enough ore to build that, and then we also want to say, okay, the number of clay robots should be less than the amount of clay it takes to construct an obsidian robot. This is the only really use for clay we have. If we have enough clay that we can build an obsidian robot every turn, if we wanted to, then there's no need to build any more clay robots. So that's our other condition, and again, it looks very much the same in terms of what the new search state is. Increment clay robots, ore goes up. And then we have the same thing for obsidian robots. For geodes, we need to have enough ore to construct it, and we need to have enough obsidian. So there are 2 resources for these other ones. But for geode robots, we're not going to have a second pruning condition. We always want to make more geode robots as long as we're able to do that, because that just increases the number of geodes we can get, and that's our goal ultimately. So this is how we calculate all of our neighbors. We do this cat maybes on all of these different maybe steps. Put that all together, return a list of those search states. So Now, the last subtlety is we're doing a depth first search DFS instead of a breadth first search DFS. Why are we doing that? We aren't going to be able to do that previous max trick if we do a breadth first search, because we're just counting the maximum we can do in 24 time steps, and if we're doing a breadth first search, we're not going to have any final answers. We're not going to have any maximum until we get to the very edge of our search space, and so we're not going to be able to use that as a pruning mechanism. However, if you do a depth first search, ideally we will be able to find fairly early on a reasonably good number of or at least a path that gives us a reasonably large number of geodes, and then we'll be able to exclude a lot of other paths along the way, paths that don't give us as many geodes. That's kind of the idea. Once we have one reasonably good end state, we can start doing a lot more exclusion in the rest of the search. So most of this function is just the basic way you would write DFS. It uses a stack, so we just have a list of search states. If we're out of states to search, we just return the previous maximum. Otherwise, we have a state that's on top. If it's beyond the maximum time, this is another base case. We just return either the amount of geodes in this or the most geodes we've previously seen, so we have a maximum operation there. Otherwise, we get our neighbors, and then we filter those neighbors. We make sure we're not searching the same state twice. Always important in any kind of search. Otherwise, you'll be going in loops. Not super fun. Although it's probably not such a big deal here because we're always incrementing the time step. Actually, no. There's definitely some ways we can overlap. So it's a good thing we're doing this. So we construct our new visited set by inserting the neighbors, and then we just do a fold. What's this F doing? So F takes the previous max and the new visited set. These are its parameters, and it recursively calls DFS with, we have our maximum time parameter. We have BP. BP is our blueprint, and we have a previous max, and we append this state to the stack. And then we just, at the end of the day, we return the maximum of this resulting value and the previous max. So that's sort of that's the way we invoke recursion, and we use a fold so that we can keep passing that that maximum value through. That's how we thread it through the different recursive calls. So this is our depth first search. Now we do a fold through all of our different blueprints. I forget, so line type is just a blueprint. And so we get our quality score by running our DFS with 24 steps with an initial maximum of 0 and our initial state. And then I think we take our previous quality score. We take the idea number of the blueprint. Remember we stored that at the beginning, and then we multiply that by the number of geodes we get. And so we just add all that together. And then when we've done this for every blueprint, we get our final quality score. So that's the end of part 1. For part 2, it's like nothing really changes all that much in the algorithm. We're just doing 32 steps, but we're also only using 3 of the blueprints. So it gives a little bit of a break. It takes longer to do 32 steps, obviously, but when you're only doing it 3 times as opposed to 30 times, your algorithm will still do okay. And at the end of the day, we just multiply those 3 numbers together. And so that is enough to get us our answers reasonably quickly. This isn't an instantaneous solution. It's a pretty big search space, but it doesn't take too long for us to get our answers using the solution. So day 19, one of the harder problems, but once you have a lot of experience with graph algorithms, then you start to get an idea of what to do here. So if you're enjoying these videos, make sure to subscribe to this YouTube channel and to subscribe to the Monday Morning Haskell email list as well. Link for that is in the video description. So I'll see you soon with the next video.